Great pleasure to have Niki Vazou here together with us. So Niki is Associate Research Professor in IMDEA in Spain, and she did her Ph.D. in UC San Diego and her diploma in National Technical University of Athens. She visited us here for a couple of weeks. She will talk about refinement types today. So Niki, among other awards, she has also she runs an ERC Starting Grant in IMDEA. So looking forward to listening to you.
Okay, so thank you very much. Yes, today I'm going to talk about refinement types, and as Nico said, I did my diploma at ECE and UA. I got in 2011, and then I did a Ph.D. in UC San Diego at the same time as Nico's, and then I did a 2-year postdoc at University of Maryland, and currently I am at IMDEA in Madrid. And all of these years I have been a very active member of SIGPLANT, which is a special group of programming languages of ACM. So SIGPLANT has 4 main conferences. I published all of them, which is interesting because POPL is the most theoretical, PLDI is the most applied, and my area ranges to all the areas of programming languages. I have served as a PC member to all of them. And this year I was actually elected in the executive committee of SIGPLANT, which is very exciting. So I do programming languages, and especially I work on program verification, which is the area that uses static verification. So before we run the program, while we are developing it, we want to check that the program satisfies certain properties. And the goal is to ensure that there are no bugs, that the quality of the code is very good, and also, hopefully, we can speed up the code. And so the way I do program verification is using this technique that is called refinement types. And in a nutshell, refinement types are type-based, and we use SLT to automate verification. And what is very cool for refinement types compared to the other verification techniques is that the goal of refinement types is to extend and make more safe and verify code that is already developed in existing programming languages. And so here is an example. So I have a type in an existing programming language that is indexing a list. So the existing type of indexing says, give me a list that has the elements of type A, give me an index I, and I'm going to give you back the ith element of the list. And what I'm doing is I am refining this type for list indexing, and I'm saying I'm going to name the input list x's, and I'm going to give a refinement type for the index I, that says that this index should be within bounds, right? It has to be greater than or equal to 0 and less than the length of x's. And this is like the basic of refinement types. It's a very important property because it ensures that every time I'm indexing lists, I cannot get out of bounds, which means I cannot access things that I should not access. And yes, the program is safe.
Sorry.
Yeah.
Isn't it something that the compiler should do, right?
Yeah. Everything happens at compile time.
Okay, so this is not verification, this is compiling, right? I mean, a plain compiler should check whether I is within the nominal range or not.
Most compilers don't do it.
Don't do it.
Most compilers don't do it because...
I haven't been programming since 30 years ago, so I don't remember, but I thought they did it. No, they don't.
Most compilers don't do it. For example, this language that I am using is Haskell, and by default it's not doing it because the problem is that if you are going to run these kind of checks, you need to provide a lot of information that these checks pass. Right? You need to do reasoning. And the programmer usually doesn't want to do this kind of reasoning. So what we do is we use solvers to do this reasoning automatically. But it is compile time in the sense that it's static, as we call it. It is verification. Yeah, and if you have other questions, feel free to ask. compiled for a program for a long time. I'm going to show you these refinement types.
Okay, yeah. Start from the basics.
Yes. So as I said, so I'm working on Haskell. This is what this HS stands for. It's Haskell. And yes, I'm just running Haskell here. Cabal is the environment that builds the Haskell development. Yes. I'll try. And so on the back here, I'm running my refinement type checker. It's called Liquid Haskell, and the cool thing is that it just extends the current verifier, right? So as I said, list indexing has these conditions that it has to be between 0 and the length phi. So if I just say, okay, go take the ith element of the list x's, I'm getting an error. And this is like, I mean, the Haskell compiler does not complain. But on the back, we use the Liquid Haskell and it complains and says, for example, by the refinement type of indexing, it has to be greater than 0. So what I can do is I can say, if I is greater than 0 as you want, then do just this, else return nothing. And I am returning a maybe integer now, so I have to specify that. And the error changed and says, okay, now you are bigger than 0, but you have to be less than the length of x's. So I have to say, okay, it has to satisfy greater than 0, and I needs to be less than the length of x's, right? And now the error got away. And yes, so safe indexing now is good. Cool. And this is one of the built-in operators that comes with refinement types. Another one, for example, is division. Because as we know, division by 0 is very bad. So if I just say, okay, go and divide the result with 42, divide by whatever you index, I get again a refinement type error that says the divisor cannot be 0, right? I have a value for the divisor, and you need to prove me that this is different than 0. And so this is like something that refinement types are really good at. We can, like, to allow this division, we can use refinement types to say that all the elements of the input list are different than 0, right? And for that, this is my Haskell type. So I can use comments to give a refinement Haskell type and say my input is a list, and I can refine the elements of the list and say that the elements of the list are called V, and all these V are different than 0. And the error goes away, right? Because all the elements of the list are different than 0. Okay, and now we use refinement types to specify the input of my test. And since we did that, we wrote the type, we can go further and say, okay, like my input list is x's, and my index is a value such that this value is positive, and also v is less than the length of the list. So exactly what I need, right? And with that, I don't have to do the runtime check. Okay, so now, like, indexing is fine, division is fine, everything is fine, because I put the check here. And this is what I mentioned before, that with these refinement types, your program can speed up because you are allowed to remove runtime checks. Right? Questions? Yes.
Again, just since on my case as well, like I'm a little bit far from software engineering, so just really from the view from the space, let's say, still kind of to understand what's the difference between, you know, what the compiler will do and what this adds extra. So for example, I write code, I write some things, I might make a mistake in the code that I have entered. The compiler will just give me, okay, you have a syntax error there, or it might tell me, okay, division by 0 or something like that. Actually, division by 0 will find it in runtime, right, not in the compiler.
And indexing, yeah.
Okay, so now what you're doing would do what? So I will write the program myself, and then I could go and compile it. So where does this, let's say, work come into the picture? Is it something that will simplify, will basically allow me to code something without even doing the mistakes that the compiler will find, or is it something that makes differences in the compiler? Apologies if the question sounds super naive.
It's not. It's not. So the thing is that the compiler is checking whatever you tell it to check, right?
Mm-hmm.
Most compilers check that the structure of things matches, that you are not going to
The
add
syntax,
integer.
let's
Yes,
say,
syntax
yes.
directly.
Okay.
Yes, exactly. That is, I think that is the critical point. That most compilers checks the syntax of your programs.
But then at runtime, the compiler might say, okay, but then I run it and it comes up without a mistake. So this is what we're trying to see if the program would actually work at runtime in some sense.
So there are two things. One is that you basically here in the refinement you put logic. So you go into the semantics. You can tell the compiler to check things that they cannot be expressed with the syntactic types.
Okay, so then you offer essentially this, you're trying to somehow make the compiler smarter, but essentially with input that will be difficult to put into the, let's say, compiler code in some sense.
Yes,
Yes.
the current structure of the compilers, like, it can distinguish integer from strings, but it cannot distinguish different than zero than
Okay,
with the rest of it.
I think I'm
So-
closer now to getting it.
So yes, so here we put logic, and with logic you can express whatever you want.
And in practice, you compile the code and then pass it through this filter as a second step to check for logical errors.
Yes,
Okay.
and concretely we use SMT to do the checks, and that's the point. Like the most refined or expressive your types are, the most difficult it is to do the reasoning. So we use the SMT to do all this reasoning for you. And yeah, I think this is another key thing is that this holds generally. The compilers and I call it the type system, but yeah, the compiler is the same. It checks whatever you tell it to check. And the more refined the checks are, the more annoying they are, because the programmer doesn't want to reason about this. So most compilers say, okay, like I'm just going to do the basic stuff for you. And like yes, we come and we can refine this more. Okay, and this is like the basis of refinement types to do this kind of like light tests. I can quickly show you most of my work I have been trying to extend this kind of reasoning to what I call deep reasoning. And here I am using the same concept of refinement types to prove more sophisticated theorems. And I'm going to do this fast. But so, we use types to express the standard theorems. For example, here I'm saying I am going to define the theorem. It's called right identity. That says that for all x's that are list, if I append to x's the empty list, I take back the empty list. And this comes with an inductive proof. And so to prove this theorem, I have to basically do the mathematical induction that we learned, and I am saying if the list is empty, then I am going to give you some proof, and if the list is a cons, then I am going to give you some other proof. And yes, now I'm getting errors because it says that I cannot prove with the empty proof is not enough to prove the property that you want. And you can actually go and do mathematical proofs using refinement types in programming language and say, for example, okay, in this case x is empty, so empty append to empty is equal to the empty list, and then this concludes the proof. So now my error went up, which means the first case is fine. And okay, I'm proving the inductive case. And Copilot knows most of the things. So append x to the list the empty. I take the first element out. And here, to conclude my proof, I am going to do an inductive hypothesis, which is by calling my inductive function, and the proof goes through. And this is quite a cool feature because basically you encode mathematical proofs using refinement types in an existing programming language. And so now, like, these steps are kind of boring. So in Liquid Haskell we have developed a tactic called PLE, logical evaluation, programming by proof by logical evaluation. And if I activate PLE, then I greatly simplify my proof and say, okay, in my base case it's trivial, in my inductive case I just need the inductive code, and the proof goes through by case splitting. I have to prove a property on list, I case split on the two structures of the list, I do an inductive call, and my proof goes through. And yes, let me go back to the slides. Questions here? Okay, so how this works? So refinement types is basically this black box that takes as input some program and a property. And what refinement types are doing is basically they want to prove that the program satisfies the property, and to do that they generate logical formulas that they send to these SMT solvers, where SMT solvers are tools that we treat as black boxes that automatically decide the validity or the satisfiability of the formulas. And yes, in the example that we saw at the beginning, my property was safe indexing, so I want to check if I can index x's with an element I. And to do that, the logical formula is going to check if from whatever information I have from the environment, I can say that indexing is fine, which means that my index I is between 0 and the length of the list, right? And we saw that if at the beginning I have 0 information from the environment, then I cannot prove it. So SMT is going to say no. But when we put the if, I have exactly the information that I need, right? So the formula is like valid, trivially valid, so the proof goes through. And refinement types have many nice features. They are case sensitive, which means that when I have branching, when my flow splits, the type checker, the compiler, knows exactly what is happening inside the branching. Right? It also is type-based. So as we saw, we can define collections like lists of elements. So using the structure of the types, I can inject logical formulas. And what else? It is decidable. Decidability is very important. So everything that we send to the SMT solver is decidable, because whatever I send to the SMT solver is generating by my refinement types. And this is very important because if you ask to the SMT solver questions that they don't know, we have what we call the butterfly effect, which means that I have a big SMT query, and I can change something somewhere, and then like undecidability comes, and you don't know, like you cannot control it. It says, I don't know, you have no idea how to fix it. And yes, so like this is a big constraint that we have in refinement types, that everything should be decidable, but then we also want to prove these like deeper properties like associativity. And to do that, between the SMT and the refinement types, we have generated various tactics. So, like I briefly saw you the proof by logical evaluation, that is just like unfolding steps. And we have another one that we call REST. And this is very cool. So, so REST basically instantiates axioms that we have in the environment. So for example, if we want to prove distributivity, we can say prove it using the right identity that we saw and associativity. And like this REST is a very nice verification technique that is using online termination to do like, again, like decidable and efficient axiom instantiation. And what I like very much about this technique is that we developed it for Liquid Haskell, but it has application generally in the rewriting theory. Okay, so yes, we are decidable, which is very important for practical usage. And the last thing that is very nice about refinement types is that it's language integrated. So all these refinement type checker becomes part of the compiler, like that we saw. Haskell, you can extend it using refinement types, and like this being part of the compiler has many benefits. So you can use it as an editor plugin, you can use it in cloud support. Every functionality that the compiler gives you, you can extend it with refinement types. And so with all these features, I can conclude that refinement types are what we call practical. Unlike other verification techniques, they can be used to extend an existing programming language. And in the rest of the talk, I'm going to discuss other features of refinement types, for example, if they are expressive, general, and if they are sound, what we call. Okay, so expressive.
Question?
Yes.
Go.
No, you first.
For different languages, do we have to develop different?
It's here.
Okay.
Okay, so actually this I'm expecting this to come later, but in principle for now you've shown somehow some handmade rules, right? That you as a person, like, to what extent can someone automate what you might need, right? Like, is there a way to, because this, if I understood correctly, right, you come on top of the compiler and you somehow create some additional rules to make the compiler faster, make the, you know, like the editing better, but you as in someone has to come up with these rules, right? These are not automatically made, right? So there must be a library or people that understand what might go wrong will have to go and enter the rules.
Who enters the rules?
So the question is, who enters these extra rules? Is it a human? Is it something that can be automated with all the crazy machine learning stuff, etc., or?
We
Am I really off?
we have stayed up to now very separated from the machine learning.
Okay. Good for you.
I don't know. I mean, there are some words, but not on the rules. So yes, I think like again in general. So depending on what you want to do and what you want to express, what language you are dealing with, there are some like the refinement types are basically an inductive set of rules, like that generate like this. You take the properties, you take the program, and you generate a verification condition. And I guess your question is how do you generate that, right?
Yeah, exactly. So again, if I can make the analogy with the machine learning a little bit, so you know, the whole idea is that, you know, machine learning used to be about picking features, right? What you think is important, and then on top of these features, you have the algorithm that does the rest automatically.
Yeah.
And then there is all this new, let's say, age of machine learning, which is featureless. It will figure out what features to do.
Yeah.
So the way I see it now is that some of these are, in some sense, features that you, I mean, or the one that knows the language will have to pick.
So I think the main difference is that in program verification we go for this property that we call soundness, which means that if the tool says you're good, you have a proof that your program satisfies the property, like for sure, right? And machine learning doesn't have that. I think like
So
machine
you don't have false
learning
positives, let's say, in some sense.
yes,
Yeah,
yes. We can say no and it can be yes, but like this is the sound that all the type systems need to satisfy, right? So what we do in general is we construct the rules and then we prove the sounds. And this is not easy to make it correct. We have like, again, like in general I mentioned, we have written with my PhD supervisor a tutorial how to make refinement types for your own language. Yes, there are some basic strategies that we know how to make them, but it's not easy in the sense that, for example, Liquid Haskell was unsound for a long time. The first versions were wrong, the rules were wrong, and so yeah, it's not easy to generate the rules. Every new language and every new feature that you want to add may go outside of soundness. So yes, like it's more experience in that like
There is a little bit of art involved, let's say.
there is art and the structured way to do. Yes, there is the experience that like I know like, and if you give me a new language like I have worked on refinement types for other languages, and I say, you know, like in Liquid Haskell we have this, so you should expect this. But then like the structured way is you design the rules and then you prove that they are sound with like extensive proof. And if the proof doesn't go through, you go and you reiterate the rules.
Okay, cool.
I'll make a simple question, as simple as I can. I'm writing a code, and at some point I invert a matrix.
Mm.
And someone must check whether the matrix is singular or not.
Mm.
The compiler does not do it, right?
Mm.
Is it correct?
Yeah, the compiler doesn't.
Okay. Then this something like a refinement type will check it, right?
You can do.
Okay. Who is going to add
Write the
this check
specification.
to the refinement type? I'll do it while I'm writing my program. Since this is something common, I guess that somebody has to do it, and then this is something that goes together with the product, with the compiler.
Yeah.
Right? So, at which level it is based on the programmer, and at which level it is based on something general that any program, any compiler should be affiliated with.
So right now it's everything is on the programmer.
Okay, so
And,
so if I program something, if I write such a code, I will add this refinement type.
You have
Then
to
if
add
I
the
is
refinement
write
type.
the code, he has to do it again.
Yes, and
Oh.
the correct way is you develop your library that inverts the matrix, and you put the specification on your library. So when Akis is using this library or he is changing it, then he needs to not break your specification.
Okay.
But so like right now, refinement types, the major refinement type of work is checking the specification, and actually writing the correct specifications is a very difficult problem. And as far as I know, it's like a good use of like there is a work like 2 years back, I think, learning refinement types that is trying to infer your specifications. But this is difficult because like you need to understand what is in your mind to write the specifications.
How about writing the specification, not for a specific language, but then somehow automatically convert it to refinement types for its language separately. So I write the specification for the matrix inversion. The matrix has to be checked if it's singular or not.
Mm.
Okay, this is the specification, the rule.
Mm.
Okay, is there an automatic way to convert this rule to something like compiling on the compiler of its language?
I don't know.
This would be very useful because I don't want to
I think this is
get involved with the details of the language. I just will set the rule.
like I'm not aware of this word because I think you're saying like go from human language to like this is formal. This is quite formal. And as far as I know, this is a difficult problem.
Okay.
Yes, like dealing with natural language hasn't reached the area of program verification yet. There is another direction that is more explored, that is if you write the refinement type specification, how do you synthesize the code to generate the program? And I think like this is easier for us that are more like structured mathematics because at the point that things are well written in a formal language, it's easier to change the type and the program for us is like very the same thing. So yes, but from human to formal refinement types, I'm not aware of it. But I assume it is like AI aided, it will go this way. Good. Okay, expressiveness. Okay, so we said that we are using SMTs. SMTs only work well when you are in the decidable theories, and there are things that are easy to express when you stay in these decidable theories. For example, safe indexing, we see sortedness we saw. And then the question is, can we can we also express more sophisticated problems? For example, like what domain-specific properties can we express? And an area, a domain-specific area that I have worked a lot is this secure web applications, because it has like interesting properties and they are more, again, well-defined and they are quite challenging. And the concept here is we have a program, there is a database, the program manipulates data from the database. And so what is interesting is that this database can have protected data. So for example, I can have passwords that are secret, and then I have like usernames that are public. And so we have this property that is called non-interference, that says that secret and public data cannot interfere with each other, which means that if I don't have access to the secret data, I should not be able to see this data, right? And so there is an application we developed. It's called LWeb, and LWeb is using runtime checks to ensure non-interference. And what we did is we use the refinement types as a theorem prover, as we saw with the associativity proof, to actually prove that LWeb satisfies non-interference. And exactly the proof says that the execution preserves the log U. And what is log U is like I have a program, the program executes and generates a value V. And this program satisfies the log U equivalence if we erase all the private data that the program doesn't have access to, the value remains the same. And we encoded this property as a refinement type. So the non-interferences for every program P1 and P2, if I erase all the private data from P1 and P2, then their execution remains the same if I erase again all the private data. And we used Liquid Haskell basically to prove this non-interference of LOL. This was the first major Liquid Haskell proof, 5.5K lines of code, and we proved that in a model of LOL that is using dynamic runtime checks to ensure non-interference. And then again, like secure web applications is an area that I like a lot, so like I have collaborations that keep pushing in this area. So in a very similar way, we have Storm, and the idea here is that now the checks happen statically, and so the refinement type checking in Storm ensures non-interference. The private and public data are not going to mix with each other. And then we did ANOSI, again, in which refinement types track abstract domains that capture how the information and the policies run in your code. And as a final line of this line of work, with my PhD student Zegarelli, now we are working on how do we ensure, again, this kind of policies, but they are dynamic. So data can be public or private, and this changes. And so this is an area, a domain-specific area, which we use refinement types to capture secure web applications. And here are two other examples of domain-specific properties that you can encode using refinement types. So we have used refinement types to see resource usage, how much resources a program needs to get executed, and to verify distributed applications. So in short, refinement types can be very expressive, and there are these decidable trivial properties like safe indexing that just work out of the box. If you run now Liquid Haskell, it's going to prove automatically safe indexing or division by zero or other like properties for you. And if you try enough, you can encode domain-specific properties, but it's not trivial, but it is possible if you're willing to encode properly your specifications and make the proofs for you. So yes, refinement types are quite are they general? Like, this was the question before. So, like, I mainly work for refinement types for Haskell. And the story here is that the refinement types started from a programming language called ML from OCaml. And the first paper we had on refinement on Liquid Haskell was 14, when we just started to port refinement types from ML to Haskell, and there was a big error. Like we made the typing rules wrong because Haskell has this feature that is called lateness, and like all the typing rules for ML broke when we port them to Haskell. And since then there are refinement types for Rust that we need special rules to deal about how the memory is managed, because Haskell and ML essentially do not have memory. There is a group at EPFL that is designing refinement types for Scala, and hopefully in the next version they will be part of the language. And there was recently a paper that was developing refinement types for WebAssembly, which is another very different language. And as I mentioned before, the principles of refinement types are quite general. So if you are in a very restricted fragment, we know how to do it. But then every language has their own feature, so you need to adjust the rules based on the dynamics of the language. And there is a tutorial on how to develop refinement types that actually I think it has helped many people understand how to design their own refinement types. Okay, that's about generality. Any questions? Okay. Okay, so let me talk about soundness then. So yes, I mentioned it before. When you design a type system, you want it to be sound. And informally, this means that the type system actually checks what it's supposed to check. And formally, we say that the type system is sound when it totally accepts programs that cannot get stuck. And this stuckness is a property that we have there to express the mathematical definition of soundness. We say if a program type checks, it has a type E, and this original program starts executing, starts evaluating, then it reaches an expression E that either is going to be value, it's going to return, let's say, 42, or evaluation keeps going, right? So if a program type checks, it cannot crash, it cannot divide by 0, right? It has two options, either run forever or return a value, and this is the value that we want. And this is a nice mathematical property, right? So what we did, published like this here, we took this property, we made it a refinement type, like you can, like I saw you use refinement types to encode associativity, and we use Liquid Haskell to prove a model of refinement type checking is sound, satisfies soundness. And this is like the biggest Liquid Haskell proof that we have done up to now, 10K lines of code. And so with that, let's say we prove that Liquid Haskell or refinement types is sound, right? Because we have proof, and this is like the core of the proof. So we proved it sound. And but that is not true. Because like we have the nice mechanized proof, right? But in practice, refinement types has every software, right? It is unsound, and in practice, we know that because in Liquid Haskell and like I did some searching when I wrote that, but also in other refinement type checkers because there exists more. We get about 5 unsoundness reports a year, where an unsoundness report is that some user comes up with a program, and Liquid Haskell says yes, the program is correct, but at runtime actually the program violates the property. And this is too many if you compare it with other verifiers that are designed to be sound. For example, Coq.
Sorry, question. how can it happen if we can guarantee that the rule is checked and the compiler, the refinement type checker, will reply if the condition is holds true or not? Okay. So this is something that deterministic. How can you get 5 reports per year on programs that pass the check while they violated the rule?
Yes. This is, I will respond to that. Give me
Okay.
2 slides. But I mean, for me, that was expected because I am like one of the main developers of Liquid Haskell. So
Yeah,
I
know that for you,
I
it's
don't-
expected, but it's not expected for me.
Yes, so what was more like what I had your reaction in that? So Coq is a data verifier that is supposed to be, it's supposed to be like, I mean, Coq is what even companies now use to prove correctness of the software. And the Coq that people report like about unsoundness bugs per year, and this is what I found surprising. So in Liquid Haskell, this is why it's not sound, right? So Liquid Haskell implements core, implements like something. So core is what we formalize. And we know like this is what we prove, we know exactly what is happening here, we know exactly the rule. But also it has many features that we don't fully, we have not mechanized. We have the rules, but we don't have a proof, like in the model that we proved, we don't know exactly what is happening because it was very difficult to port the model. Because Haskell is a big language, it has these fancy features like data types, it has inference questions. So these are features that we have not yet mechanized. So we are not exactly sure what are the semantics of these Haskell features. So we have no idea what are the semantics of the Liquid Haskell features. And this is not our problem because Haskell and most programming languages don't come with formal semantics. So it's very difficult to understand how they, I mean, C is, I think in C there is a common example that you run it and you don't know exactly what it does. And so this fancy feature is like mostly the source of our bugs. And then there is the implementation. The implementation is huge. Like we trust all this implementation. And yes, like since you asked, I can also tell you that in some of these bugs it was the SMT solver was wrong. I mean, in software it has these problems, right? Okay, so the situation in Coq that is designed to be sound is like it's still improver that we all trust is much better because Coq has a trusted code base that is much smaller, only 15K lines of code. And it implements what is called calculus of inductive construction, which is a theory like similar to what the refinement types are doing, but it's like different because it's designed to be sound. And this theory reduces to set theory. And because we know that set theory is consistent and there is a reduction from CIC to set theory, we know that CIC is sound. And so the only like a code has like this 1 bug per year, because there is something wrong happening here. And yes, like so the Coq people have started a project that they are again trying to formalize, mechanize the soundness of their implementation using Coq themselves. Okay, so the goal that I am working on right now and what is my ERC on is how do you make refinement types, how do you keep the practical aspects of refinement types, but make them sound. And the concrete first step that I am working on now is reduce basically refinement types to the sound code. And the problem is that these are 2 different different systems, so the gap between these 2 is big. So yes, like early work presented in types 23 is a work that I'm doing with 2 of my students right now, that we are basically trying to generate Coq verified files from files that refinement type check. And another idea that I have and I'm glad to work on is to design this logic of refinement types that is very similar to CIC, to the logic of Coq, so that we have like a very small trusted base that we can develop on. And I think this is very cool because refinement types are practical, and but because they're designed to be practical and to use to be developed on top of existing languages, but they don't have these like foundations that comes with theorems like Coq. So I think like developing these kind of foundations is really important. And yes, my aim is to like deal with this unsoundness of refinement types. And thank you for your attention.
So any more questions for Niki?
Have some, but yeah, let's
Yes.
another one.
What's the mathematical background of your profit logic or something else?
Of
The mathematical background of your structure, of your is it logic? How
refinement types.
yes.
So I mean, I can tell you that of Coq, for example, is set theory and it is
Set theory.
logic. Yes. Yes, I mean, Coq has constructive logic. Refinement types, we are like I am in the process of setting the background right now because we like it combines these inductive rules that generate logic with classical logic that we ask to Z3. So it's not defined.
How do you make a sense of that?
Somebody else?
Okay, so first of all, thanks a lot for a very interesting talk, and apologies again in advance for the questions that might sound a little bit naive. So the first thing is that this is more philosophical, right? So this is the same background as automated mathematical proofs, this whole story of decidability and whether the system is completely correct and all that, right? Which means that in theory, it's a tough problem. It's in principle, in theory, you cannot solve everything. Correct?
No, we're not going for completeness.
Yes, that's what I'm saying. Anyway, theoretically, I mean, technically it's not possible, but it's a tough mathematical problem how to automate essentially a system that you solve the rules and whether it's something decidable or undecidable, at least for mathematical proofs and for systems. It's incompleteness theory, if I'm not mistaken. So but I'm guessing that the theoretical part of all this work has a lot of, let's say, overlap, and maybe this is what Fanas was asking with the people that are doing from CS or math that are doing really logic and, let's say, automating mathematical proofs, right?
Yeah.
Okay. And the second thing is more practical. So essentially, now I think I have a better picture. So who would be interested about this? Essentially, if I'm a company, let's say Amadeus or JR, and I'm building a transaction software, right? And okay, compile to me, it seems correct, and I will sell it to all of you. Somehow I want to make sure that when you run it and you run a business of millions, it's not going to crash by something or do something that I wasn't expecting. So essentially, this is kind of an extra check for me and to show off to my clients.
Yes.
That, okay, this thing is safe, it has passed this and this check, so you can safely run it and it should deliver what I promised, right?
So, I mean, okay, let me comment on the first part.
Okay.
So, on the first part, I think historically it is what you said, right? There are the mathematical foundations like CSE, calculus of constructive inductions that came from set theory. But it is, I think it's important that they, like them, Coq, and the mathematical people come from a different direction. They say, this is our theory, we're going to implement it. Like Coq and the most formal verifiers, they don't have runtime semantics. They don't care to be integrated to programming. Refinement types say, okay, there are all these nice verification problems. Nobody is using them because it's a different language. So what we're doing is we say, here's a language, I'm going to put logic on top of it and make something practical. I think this is the big distinction. And this is why we don't have the mathematical foundation yet. Because we want to try to catch errors on existing programs, on existing language. So it's, different direction. And yes, it's what you said, I agree that if you are a company and you have the stamp that your program is verified, I think this is a big sell for your clients, and I think, yes, companies are interested about that. I mean, I see it more idealistic. I do believe that...
It is possible to stamp, say, commercial products to say that I stamp is correct based on my approach?
Yeah, I know
Is it
that.
possible?
I know that with my tool, or it's in general, so I know that people hire code developers just to put a stamp.
Okay. Good business.
No, because it's I mean, they implement things, and then they have the code people verifying models of them, and then they have a stamp that yes, like we have code developers. Yeah.
It's better than hiring a million testers, I think.
Yes,
it
yes.
automates,
Yeah, and it is important. And I mean, at least 2 years ago, with all the crypto people, most crypto people had formal people who work on formal methods because it was.
So what is the final goal? For example, as I said, you cannot solve all problems.
Yes, that was the other. So I mean, so there are the two things. There are the problems that refinement types are very good, like indexing this, that it just works now, and then like on the expressiveness. I believe I know how to make proofs of things that are not automated, like all these, like the web applications, like which is what I proved, the way I proved associativity. To prove something, you had to do the inductive proof as a user. So if you are willing to do proofs manually, you can, like refinement types can use to be checked. But by default, like when you say prove me associativity, it is going to be, it is going to say I don't know. And then you have to do the inductive call yourself, and it's going to prove it. So I don't know exactly, like refinement types have this very strict rule. Everything that goes to the SMT solver should be decidable, which means that it should, like syntactically, you cannot write stuff that go out of this fragment, because otherwise SMT solvers become very unpredictable and you don't know how to deal them. And then if you want to prove sophisticated properties, by default, the checker is going to say no, and you need to do the inductive call yourself externally. Yes?
So is it well defined the class of programs or problems that we can guarantee that are correct, or this is your goal?
The automatic ones,
Yes. Is it well defined? I mean,
there is it's not defined because we ask queries to the SMT solver. So you can write theories that the SMT solver can define. For example, like recently, 3-4 years back, the SMT solver can reason about data types. So then we extended Liquid Haskell and we say, okay, now you support, like in your refinement, you can use properties from the elements of the theory, from the theory of data types. So it's not well defined.
Any other question? Okay, thank you very much.